studied TCA cycle. Okay? Or you should have at this point. We've studied it, so we know. The only distinction is that there's a cytosolic form of it to reconvert the malate back. So you could argue, well, why don't we just move the oxaloacetate through, right? But if we did that, we wouldn't be moving a reducing equivalent, right? Because what we're doing here is we're moving a reducing equivalent. We're moving NADH from here to here, aren't we? I mean, we haven't taken NADH and physically moved an NADH molecule, but that's effectively what we've done by virtue of the enzymes that are running first in one direction and then the other in the different compartments. Right? Does everybody see that? So we have moved reducing equivalents back, and we have to, because we can't run step 6 of glycolysis backwards like we have to if we don't have NADH. Right? That gets formed in glycolysis. Questions? Pretty cool, huh? You give it, I mean, you give the cell a couple of billion years, and you know, who knows what it comes up with. It comes up with a lot cooler stuff than this, but we'll get to it. Okay, and then this split off here. We're going to look at the two enzymes a little bit, not in great detail. But now you got PEP, and then you're off to the races. Now you just go straight up the pathway until you get this to step 8, and that's a phosphatase, and then step 9 is reversible, and step 10 is another phosphatase, and we're done. So we could ask, how does pyruvate carboxylase work? So pyruvate carboxylase is this enzyme here, always the same one, right? The difference here, if you come from lactate, is that PEP is formed first and then transported out. And here, the NADH is already formed from lactate, so you don't need to form it again, right? And so there are other balancing signals in the cell that say, you could argue, well, how do you know whether oxaloacetate should go this way or this way? Which of these two enzymes, both in the mitochondria, should you use, right? And that's because the enzymes are sensitive to the redox state in the mitochondria at that time, which is sensitive to whether lactate dehydrogenase has generated a lot of NADH in the cytosol. It's tricky, it's a little complicated. But the question arises if you think about this slide, like why this and not that. Right. So pyruvate carboxylase, always mitochondrial enzyme. How does it work? It works with another cofactor which we haven't encountered yet. It's called biotin, and you've probably heard of biotin because it's yet another vitamin. This is what it looks like here. This is carboxylated biotin, right? And here we've got a lysine. Residue on an enzyme, right, on the pyruvate carboxylase enzyme. So, what does this remind you of? It should remind you of PDC. We had lysine, we had lipoic acid link, we had this long floppy arm. Well, here we've got pyruvate carboxylase, we've got a lysine, we've got a floppy arm, and now at the end of the arm, instead of lipoic acid, we've got this kind of biotin thing hanging out, right? It's got a sulfur in it, some nitrogen, and there's the CO2 getting attached. And this enzyme is going to work like PDC did by way of taking this tethered group here with this floppy arm, not as long and floppy as, or actually it is as long as floppy because you've got 1, 2, 3, 4 methylenes in here, and you got the methylenes of lysine. So nice and long and floppy, just like PDC, flop it over into another active site. So you've got two sites, one to carboxylate biotin, and the other to remove the CO2 from pyruvate, or sorry, to add the CO2 to pyruvate from the biotin. So biotin is a 1-carbon carrier. Okay. So TPP was a 2-carbon carrier. Biotin is a 1-carbon carrier. There are other 1-carbon carriers that you should hit at the beginning of next term when we talk about the synthesis of nucleotides. Okay. So here's a mechanism. I don't think it's necessary to go through it. There's not that much that's new. Bicarbonate, remember, is the form and solution. It uses ATP, right? So there's the use of ATP here. And the reason the ATP use is actually used to activate the CO2 is to get this carboxyphosphate compound. And then from the carboxyphosphate compound, you can have PI leave, which is a good leaving group, and that drives the formation of this covalent bond. It's written out in a couple of steps. But the consequence is carboxybiotin. Okay? Then you have the movement into the other active site, and then you have the transfer of the carboxy group to pyruvate. That eats up 2 ATPs for glucose, or 2 ATPs if you think of one molecule going back through the pathway. This reaction here, oxaloacetate to phosphatidylpyruvate, also requires a high energy cofactor, in this case GDP, to drive the formation of that. Yeah?
Sorry, does the pyruvate, is that attached anyway to the carboxylase, or is that just diffuses into the active site?
That diffuses into the active site and reacts, yeah. Another question? So, here's a summary of these reactions. So we're not focusing much on those two mechanisms. But this is gluconeogenesis starting from pyruvate, right? So pyruvate to oxaloacetate times 2, you need ATP. Oxaloacetate to phosphatidylpyruvate, CO2 comes off. Here it gets added, here it comes off. Times 2 ATP, right? It's leaving out those malate conversion reactions in the transport part of it here. Right? Because those are just one way and then the other way. The effect is to move the NADH out of the mitochondria into the cytosol. Okay, then we've got these reactions here going backwards. Notice that here we've got another use of ATP, ATP to ADP. Here we got NADH going backwards to NAD. So we've in effect given up the ability of that NADH to go off and make ATP later. And here we're hydrolyzing these compounds. So here's a sum of these reactions. To go from pyruvate to glucose, we're using up 6 ATPs. Glycolysis the other way only got us 2 ATPs. So 3 times as much ATP than we make in the forward direction. We use up the NADH here as well. So if you consider the NADH cost, then it's even bigger. Okay. And again, this is important for irreversibility in the cell. Glucose is an energy-rich molecule. We're making it from smaller molecules. We're reducing the smaller molecules in addition to putting them together. It's going to take energy. And we should use more than we need in order to make the overall delta G in the cell be negative enough so that when we're going that direction, right, it'll go strongly forward up the path to glucose. Right, so that there's that strong driving force. Remember that delta G in the cell depends on the driving force, it depends on the concentration differences. Another question?
You answered it.
Okay.
Can you just, I know you sort of just said it, but like, I'm getting confused as to which direction you're talking about, the irreversibility and the kind of net energy cost being negative, and I just want to make sure I have it clear in my head. So you want glycolysis to be, well, it is easier than gluconeogenesis.
It's thermodynamically favorable on its own because you're using the energy of glucose. You're oxidizing. The oxidation direction of reactions is energy yielding.
Okay.
And so you make some ATP out of it. The other direction is reducing direction as far as the carbon skeleton goes. And that costs energy to do that.
6.
6 per, yes, 6 per glucose. To make a glucose, you get from 2 pyruvates and 6 ATPs.
So would you say a difference of 8? Kind of, I mean, just idea in terms of energy. yield versus energy cost could be a difference of 8.
No.